All right. Hello, everyone. We are glad to have today Mokshay Madiman from University of Delaware, who is going to talk about an entropy power inequality for dependent random variables. Please, Mokshay.
Thank you, Katya. It's a pleasure to talk here. Thanks for the invitation. I'm going to present joint work with James Melbourne at CIMAT in Guanajuato, Mexico, and with Cyril Roberto in Paris. So let me get into it right away by introducing the notion of the differential entropy. So if we consider a random vector, x in Rd, which has some joint density little f, then the entropy, which is sometimes called the differential entropy in the information theory community, or it's called the Boltzmann-Shannon entropy in the functional analysis community, is defined in this way. It's this minus the integral of f log f with respect to Lebesgue measure, right? So one can think of this. Sorry?
So sorry to interrupt. Is it possible to remove the little screen at the bottom right?
Oh, yeah. Okay. Let's see. Okay, that seems to...
What if you try to slide it to the right just when it's on the screen?
Yeah, okay, that works.
Great, thanks.
Okay, so yeah, so there are some key properties of this differential entropy, and one should distinguish it from the discrete entropy, which has a similar form, but it has distinct properties. At least some of the properties are distinct. So two properties of the entropy in this setting in Euclidean spaces is that it's translation invariant. So if you shift the random vector by a constant, the entropy does not change. And it's invariant with respect to linear transformations of determinant 1. Unlike discrete entropy, differential entropy is not always non-negative, right? So the differential entropy can take values from minus infinity to plus infinity. In fact, the integral could be undefined as well. But we will generally assume that the integral is defined and so on. And also, unlike discrete entropy, differential entropy is not invariant with respect to bijections, right? Which is already clear from this remark here. Anyway, so the entropy can take arbitrary real values, but the entropy power, which is defined in this way, takes only non-negative values. So the entropy power is the exponential of twice the entropy divided by dimension, right? So it's twice the entropy divided by the dimension, where when x is a random vector in Rd. And it's very common to write these as functions of x, though of course they're not a function of the random realization of x, they're just functions of its distribution. So in any case, we can think, since, we know that in some sense, the larger the entropy, there are many reasons why this turns out to be a valid way of thinking about things, that the entropy is some kind of measure of spread or measure of randomness. And but the entropy itself can take negative values. So on the other hand, the entropy power one can think as as a non-negative measure of randomness. Yeah, so anyway, we will restrict ourselves to just minimally nice random variables, namely those with finite entropy. Okay, so we can. So why is entropy power useful? It's useful. This seems like an odd functional of entropy to consider, but it's useful because it plays the same role in probability as the functional volume to the 1/d plays in convex geometry, right? So in convex geometry, we have the Brun-Minkowski inequality, for example, which says that the volume of a compact set in Rd raised to the 1/d is super additive under Minkowski summation with respect to Minkowski summation. And that's a fundamental fact in the geometry of Euclidean spaces. and which of course implies the isoperimetric inequality. And similarly, it turns out there are lots of analogies between this geometric picture and the probabilistic picture. And the entropy power in the probability world, the analog of the Euclidean ball, which is the isoperimetric minimizer in Euclidean space, is the Gaussian distribution. And just as volume to the 1 over d is essentially up to a constant, the radius of the Euclidean ball that has the same volume as your set, the entropy power turns out to be up to a constant, the variance of an isotropic Gaussian that has the same entropy as your given random vector x. Right, so basically entropy power is to random variables as volume to the 1 over d is to sets. Right, that's the intuition to keep in mind, and that analogy is very useful. Okay, so that leads us to the entropy power inequality, which says the following. Let's recall that the entropy power is this functional. It's exponential of twice the entropy over the dimension. And the entropy power inequality says that if we have independent random vectors x and y in Rd, then the entropy power of the sum is greater than or equal to the sum of the entropy powers, right? So, of course, adding the random vectors corresponds to convolving the convolution of the corresponding densities. So this is really an inequality for the entropy of convolutions. Okay, so why is this inequality important? So this inequality, incidentally, was first stated by Claude Shannon, in his foundational work on information theory in 1948. But Shannon's proof was not complete. Complete proof was given by Stamm in 1959. And since then, many other proofs have been given, but Stamm's proof is still, a model of clarity and ingenuity. It's a very nice proof. Anyway, so the entropy power inequality has many nice consequences. Just like the Brun-Minkowski inequality in convex geometry implies the isoperimetric inequality and so on, the entropy power inequality implies isoperimetric inequalities in the probability world. For example, it implies the logarithmic Sobolev inequality for the Gaussian distribution. It also implies nice things about the central limit theorem. So let's see what it says about the central limit theorem. It's a classical fact. So this is an aside just to illustrate the importance of this inequality. It's a classical fact that if we consider densities with fixed variance, sigma squared, let's say on the real line for simplicity, then the Gaussian distribution with variance sigma squared has maximum entropy in this class. And so now, what does the EPI tell us about summing two IID random variables in the setting of the classical central limit theorem? So we're going to assume IID. So if they're IID, then the EPI just says that the entropy power of x1 plus x2 is greater than or equal to twice the entropy power of x1. But that can be rewritten using the scaling properties of entropy and entropy power in this form, right? And now you can see that this looks very similar to the first step in the central limit theorem. So in going from step 1 to step 2 in the central limit theorem, the entropy increases, or the entropy power, it's the same thing. So this follows from the Shannon-Stamm entropy power inequality, but it was shown by Artstein, Ball, Barth, and Nauer in 2004 that actually this entropy increases at every step, right? So if you consider these normalized sums in the central limit theorem, where you start off with IID random variables with mean 0 and some variance, then the entropy of these normalized sums monotonically increases. And since we already know that the maximum entropy in this class with fixed variance is the Gaussian distribution, it turns out that it increases to the Gaussian entropy. And this was shown actually much earlier. This convergence of entropies was shown by Andrew Barron in 1986. So anyway, so this is the entropic central limit theorem. And so there's plenty of reasons to consider studying this inequality, right? So one can ask, there's been a lot of work on entropy power inequalities and refinements of them, which came out of this refinement due to Artstein, Ball-Barth, and now some of them are in this paper. But all of that previous work done on refining entropy power inequalities and so on is for independent random variables. So one can ask for random variables in RD, which are possibly dependent, can we get meaningful lower bounds on the entropy power of x plus y in terms of the entropy power of x and the entropy power of y, or of related quantities, right? So there is some history here. So in 1990, Carlin and Soffer, actually proved. So they did two things. They proved refined EPIs in the independent case, so with an error term in the independent case, and also for the dependent case, they did not prove an entropy power inequality, but they used these entropy tools to prove a CLT under some assumptions, just the regular CLT, not an entropic CLT, under some assumptions. So a lot of the tools that they developed were foundational. Anyway, so they were one of the first to look at dependent random variables in this context of looking at entropy of convolutions, and no longer convolutions, just the entropy of sums of dependent random variables. Okay, so Takano, in actually this year is wrong. It's maybe I think 96 and 98, or maybe it was 94 and 96. In a couple of papers, looked at proving dependent entropy power inequalities as well. And he also obtained some results under some assumption, obtained dependent EPI, but under some, slightly complicated assumption, under some weak dependence assumption. And the weak dependence assumption was expressed in terms of something involving the fourth power of, so it's some kind of involving the score functions and Fisher information and so on, which we will talk about later. But basically, it's a weak dependence assumption, which is nice, but not too many applications of that particular condition have been found. So let me just say complicated condition. Okay, and then in 2004, Oliver Johnson came up with a very interesting idea, and his idea was, instead of relating the entropy power of x plus y to the entropy power of x and the entropy power of y, related to the entropy power of the conditional entropy power of x given y and the conditional entropy power of y given x. We'll talk about in a minute what these conditional quantities are. But he was the first to come up with this idea, and he claimed a result basically he claimed a result of the form entropy power of x plus y greater than or equal to entropy power of x given y plus entropy power of y given x under a certain assumption. But as it turned out, although some of the tools that he developed in his paper are very useful, this result turns out to have an error, right? So one can construct counter examples to it, and we won't bother to do this here, but that result turns out to have an error. And one of the things that we do in this work is to basically present a correct version of that result, right? So to specify under what assumptions one can have an inequality of that form. Okay, so in order to do that, I need to explain what conditional entropy is. So if we have random variables x and y with joint density p sub xy, then the conditional entropy of x given y is this average of the entropies of the conditional densities. This is a standard thing to do in information theory. A conditional entropy is not the entropy of a conditional distribution, but it's the average of the entropies of the conditional distributions when you average over the thing you're conditioning on using the appropriate margin. So that's the definition of the conditional entropy, and the conditional entropy power is defined exactly as before by taking the exponential of twice the conditional entropy divided by the dimension. Okay, so there's two useful facts about this. The first useful fact is that there's this Shannon's chain rule, which is sort of trivially proved. It says that, I mean, one consequence of this is basically the fact that the entropy of x given y, you can just define it if you like as the entropy of xy minus the entropy of y, right? You can use this as an alternative definition if you like. And what this means, I mean, the point is that, you know, if x and y are in Rd, for example, then this is a random vector in R to the 2D, whereas this is a random vector in Rd, right? So those are both differential entropies, but those integrals are with respect to Lebesgue measure on different dimensional spaces. And this difference is called the conditional entropy of x given y. It's also another useful fact, although I'm not sure we're going to use it in any strong way today, is the fact that conditioning always reduces entropy. So the conditional entropy is always less than or equal to the unconditional entropy. Okay, so I mean, the point of that is that this is always a weaker inequality than the original entropy power inequality, which involves entropy power of x and entropy power of y, because the conditioning reduces the entropy. So this is a smaller lower bound, but that's the in the case where one has dependence, typically one cannot expect just you know, the original EPI to hold. That's certainly false. And so it's reasonable to ask for an inequality of this type. Okay, so that brings us to our main result, which is that if x1 through xn are Rd valued random variables, such that their joint density, which is now on R to the nd, is log supermodular. I'll explain that assumption in a minute. Then the entropy power of the sum, you know, sum of all the xi's, is greater than or equal to the sum of the conditional entropy powers of each xi, but you condition on everything else. So for n equals 2, for example, when you just have two random variables, this theorem reduces to exactly what we said before, the fact that the entropy power of x plus y is greater than or equal to the conditional entropy power of x given y plus the conditional entropy power of y given x. And the only assumption here is that the joint density is log supermodular. Okay, so I'll define this in a minute, but I'll say already that for d equals 1, that is real valued random variables, any density is trivially log supermodular. And therefore, if we are considering real valued random variables, then this is a direct generalization. Since this is true for I mean, in the independent case, if x and y are independent random variables, these are just the unconditional entropy powers, and there is no assumption. The assumption is trivial because so therefore one obtains the classical entropy power as entropy power inequality as a special case of this dependent entropy power inequality. All right, so that brings us to the notion of log supermodularity. So a function u on Rd to the n, right? So which is non-negative, is log supermodular if it satisfies this inequality here. So u of x times u of y is less than or equal to u of x min y times u of x max y, where these are component-wise maxima and minima. Right. So so what does that mean? So for example, if you know x equals x1 to xn, where each of these xi's are now in Rd, right? Then x min y, x max y, for example, would be, and let's say that each of these xi's are an Rd. You can call each of these, xi1 to xid, if you like. Then this is going to be xi1 max yi1, and so on, just component wise. So yeah, so it's a component wise maximum. And the second remark is that this is, of course, the reason it's called log supermodular is because if you take the logarithm, then it's a supermodular function. So what does supermodular mean? So or submodular, which is the opposite. So a submodular function, let's say v from Rd to the n to R, satisfies that v of x plus v of y is greater than or equal to v of x max y plus v of x min y, right, for all x and y. And it's a classical fact that that v submodular is basically equivalent to the basically you have if all the, for all I not equal to j, let me just say this on, I'll just say this on Rn, but of course one can do this on Rnd too. But so for all I not equal to j, if the second mixed partial derivatives of this function are less than or equal to 0, right? So you need that pointwise. So this is a local characterization of submodularity. And similarly, one can of course give a local characterization of log supermodularity. So this is equivalent to dou square ij of log of u being greater than or equal to 0, right? So that's an equivalent characterization of supermodularity if you are looking at C2 functions. So this is similar to the local characterization of convexity, except that for convexity, your local characterization involves the Hessian of the function, whereas here you're looking at the elements, the off-diagonal elements of the Hessian, and that's what matters. It's not the positive definiteness of the Hessian matrix, but it's the positivity of or negativity of the Hessian matrix entries, the off-diagonal entries. Okay. So anyway, so that's what a log supermodular density is. And I mean, I should note that there are many examples of log supermodular densities. These come up in many settings. So examples, I mean, it's easy to see that, for example, any Gaussian with a covariance matrix, which is which has a certain form, exactly the form that I mentioned, right? We need, I mean, the covariance matrix, this assumption basically imposes a form on the covariance matrix. So you need your off-diagonal elements of the covariance matrix to be signed, and any or the inverse of the covariance matrix, I guess. So any appropriate Gaussian distribution with that class of covariance matrices turns out to give an example of a log supermodular density. But there are many other examples as well, and these come up in particular in statistical physics, because this is exactly the assumption that appears, for example, in the FKG inequality. So the FKG inequality, to prove that two random vectors are positively correlated, that increasing functions of two random vectors are positively correlated, one has an assumption, and that assumption is exactly this one. It's log supermodularity. So anyway, that's too much of a digression. I don't want to go there right now. but suffice it to say that there are plenty of examples. Okay, so so one of the key ideas that's used. So actually, before I go on to key ideas and so on, let me go back to the main result. So let's look at the main result again. It says that if you have a bunch of possibly dependent random variables, right? Dependent, but with joint density that is log supermodular, then the entropy power of the sum is greater than or equal to the sum of the conditional entropy powers, where you look at the conditional entropy powers of each summand conditioned on the rest of the summands, right? And that's the main result. So let me pause here for questions. Is the statement of the main result clear? Okay. So let's move on. So let me say something about the proof ideas behind this result. So so one key idea that is used not just in this work but in a lot of the previous work on entropy power inequalities is the notion of Fisher information. So for a random vector in RD with density P, the Fisher information is defined in this way. It's the, this is just the integral with respect to the Lebesgue measure again. And, this is just the integral over RD with respect to Lebesgue measure. And often this definition is written in two steps, right? So in step one, we can we can define the score function. Okay, so the score function of this random variable x is the function which is just minus the gradient of the logarithm of the density, right? Or equivalently, it's minus the gradient of the density divided by the density. And then it's trivial to observe that this Fisher information is just the expected square of the score function, right? Evaluated at the random variable x itself. So the expected square of the score function is, okay, so I guess I should put a norm square there. There should be a norm square. But in any case, the expected norm square of the score function is, which is also the trace of its covariance matrix, is called the Fisher information, right? So this is, just to be clear, this is okay. So the point is that the score function has mean 0, and therefore the second moment is also the variance. Okay, so the Fisher information turns out to be closely related to the entropy through the Ornstein-Uhlenbeck semigroup, and this is now a classical way to do things. So I'm not going to spend too much time explaining it. But the nice thing about the Fisher information is that it's an L2 type quantity, right? It's just an L2 norm, so that's much nicer. You have access to all the Hilbert space tools, as compared to entropy, which is an L log L type quantity and is much more intractable as a result. Okay, so in order to prove this main result, we'll break the proof up into 3 steps. So the first step turns out to be the following, and maybe I'll just directly show this version of the step. So there's a variant. So anyway, so the first step is the following. So we're going to start with, there's a lot of stuff on this slide, so let's just take it piece by piece. So this is the point of this is that we are going to get at the end an entropy power inequality for dependent random variables, but with some error term. So there are no assumptions here. This is completely general. X1 to Xn can be arbitrarily dependent, but you have some error term, and that error term could be very bad in general, right? So later on, we're going to show that under assumption of log supermodularity, we can get rid of this error term. But for now, we have this general entropy power inequality for dependent random variables with an error term. So what does that error term look like? In order to describe that, let's get into it here. So we have x1 to xn, which are RD valued random variables, and consider scalars lambda 1 to lambda n, the sum of whose squares is 1. Okay, and then we can look at yi. So yi is going to implicitly be a function of time. Okay, so yi as a function of time t is e to the minus t xi plus square root of 1 minus e to the minus 2t zi, where zi's are independent standard Gaussians. Okay, so one should think, the point is that each of these yi's, right? So each yi is interpolating. This is a standard interpolation argument that is used in this area. Each yi is interpolating between xi and zi, right? So as time goes from when time is 0, yi is just xi. So yi of 0 is just xi, but yi of infinity is basically zi. So you're interpolating between the random variable that you started with and the standard Gaussian. And this interpolation is exactly the same. I mean, these are just the marginal distributions of the Ornstein-Uhlenbeck process. So, I mean, the standard Ornstein-Uhlenbeck process has marginal distributions given by this. And so anyway, and this here is just representing convolution because the zi's are independent of everything else. The Gaussians are independent of everything else. So there's no dependent summation here. This is just independent summation. Okay, then this is sometimes called these kinds of forms of entropy power inequalities are sometimes called linearized forms. So the linearized form of the inequality that we want to show says that if you look at the entropy of this linear combination of the yi's, so the yi's have this hidden parameter t, right, minus the sum of lambda I squared times the conditional entropies, right? The conditional entropies that we were interested in, the conditional entropies of each one conditioned on all the rest. Then this difference is less than or equal to the starting difference. The starting difference that is at time 0. The starting difference at time 0 involves just the x's, right, plus an error term. Okay, and that error term looks a bit complicated. We'll come to that in a minute. But what this says is that, I mean, let's look at what happens when we send t to infinity in this expression here, right? So when we send t to infinity, these yi of t's are converging to Gaussian. And when you're looking, I mean, it turns out that in the Gaussian case, that this stuff basically just vanishes, right? This stuff vanishes. So what you get is you get that this entropy of the linear combination of the original xi's is greater than or equal to this linear combination of the entropies minus a quantity s bar, which is this lim sup of this error term, right? Because this error term holds for any t, and we're taking t to infinity. So we get this form, and then here we have these lambda i's, which are free parameters. So if you optimize over these parameters lambda I, subject to this constraint that the sum of the lambda I squared is 1, you get exactly this entropy power inequality for arbitrary dependent random variables, but with an error term. So let's look again at what this error term is. This error term is an integral from 0 to t of some object that so I haven't introduced all these things yet, but these are basically these are basically various Fisher information quantities associated to our random variables of interest. So I can expand on that. Maybe I should expand on that now. Oops. Let's see, did that work? Yeah. Okay, so what are these things? So what do I mean by I, j, and so on? So what the way we are going to set it up is so notation. Is this visible? Is this large enough, or should I write bigger?
It's
Well,
good for.
Okay.
I don't know.
Okay. So we are looking at some random vector x, which is of the form x1 to xn, and this is in Rd to the n, right? Each of these is in Rd, and let's say the joint density in Rd to the n, R to the nd is P. Okay, so now, so we can think of this as P of x, which is P of x1 through xn, right? And so now we can talk about the score function. We talked about the score function when defining Fisher information, but we need slightly more discussion of this. So we'll talk about the score function of this vector x, which is x1 through xn, is going to be defined in the following way. So it's rho of x, which is minus, as usual, grad p over p of x, right? And this lies in R to the d to the n, right? But now we can set rho I. So set rho I of x to be minus gradient sub I of p divided by p. And this is going to be in Rd, where the gradient sub I is just the gradient with respect to the ith x, right? So this is the gradient with respect to xi in the argument, right? And that itself is a d-dimensional gradient, right? So anyway, so the Fisher information matrix of this big vector x is the n by n I'm sorry, is the right? It's the n by n matrix. Is the n by n matrix with entries I sub ij of x, which is given by the expected value of the inner product of rho I and rho j, right? So you look at, I mean, these are both, you think of these as functions now of the capital X. So you look at rho I of capital X, rho j of capital X, and you look at this inner product, and that defines the entries of this Fisher information matrix, right? So so that's what these IIJs here are basically the entries of this Fisher information matrix of the random variables, but not of the random variables x, of these random variables y1 of s to yn of s, where these are the Ornstein-Uhlenbeck evolutes, right? These are the evolutes when you have added appropriate amount of independent Gaussian. So anyway, it looks complicated, but these are sort of this is the typical way in which one does things in this context, is to obtain entropies as integrals of Fisher informations. That corresponds to the fact that the derivative of entropy along the Ornstein-Uhlenbeck semigroup is a Fisher information. So anyway, so that's what these terms here mean. And right, so the error term comes, I mean, it's some kind of integral of Fisher information type quantities. All right, so that's the first step, right? That's the first step, is to prove this general dependent entropy power inequality with no assumptions, but with an error term. Now we want to simplify that error term. So the thing is that the main observation to make is that if we can show that these iij's are all negative, then it turns out that the limit of this s as t goes to infinity is non-negative, and therefore the error term vanishes, right? So the main point is that right. So we claim that that this error term, so the error term S bar is greater than or equal to 0 under log supermodularity. Or I'm sorry. What do I want to say? I guess I want to say less than or equal to 0. So that means that e to the minus s bar is greater than or equal to 1, and therefore we have, entropy power of x plus y is greater than or equal to entropy power of x given y plus entropy power of y given x, and this extra error term that was there, e to the minus s bar, you can just kill it, right? So that's the simplification. And why is the simplification achieved? It's achieved because as I mentioned in passing earlier, log supermodularity is equivalent if a function is C2, if u is C2, then u log supermodular is equivalent to the mixed partial derivatives of the logarithm of u being greater than or equal to 0 for every I not equal to j, right? And you want this for every x too. So for every I not equal to j and for every x in whatever, RDN or whatever. So so the point is that this this condition on the second derivative condition on the log of the density neatly whoops, not sure what's going on, right, neatly corresponds to exactly these terms here, right? So so those are exactly, one can show that those are exactly these terms here, and therefore this s bar is non-negative. So I mean non-positive. So I won't go through the details. So anyway, so that's how we get the but that actually that doesn't quite do it. The reason it doesn't quite do it is because what when I say under log supermodularity, it turns out that what we need is under log supermodularity of each ys. So of each ys for every s positive. Okay, so remember that ys was given by e to the minus s x plus square root of 1 minus e to the minus 2s z, right, where z was standard Gaussian, and therefore I mean, this is really asking for log supermodularity not of the original joint density, but of the original joint density convolved with an independent Gaussian, right? So that brings us to this question, namely, which we need to answer in the affirmative in order to prove our main result, which is if the joint density of x, which is x1 through xn, is log supermodular, can we automatically conclude? Can we conclude that the joint density of of basically y, which I can think of, or y of s, which is y1 of s to yn of s, right? Where each yi of s is xi. It's exactly this Ornstein-Uhlenbeck evolute is e to the minus s xi plus square root of 1 minus e to the minus 2s zi is log supermodular, right? That's what we would need. And this basically boils down to this, to the following conjecture that if P is a log supermodular density and G is a standard Gaussian density on the same Euclidean space, standard Gaussian density. It doesn't have to be, well, anyway, so right, let's assume this, then is P star G convolution of P and G log supermodular. Right, that's what this boils down to, because if we can show that the convolution of the standard Gaussian is log supermodular, then by a homogeneity argument one can show that, by a scaling argument one can show that convolution with any Gaussian, any scaling of the standard Gaussian is log supermodular, and therefore one would have this result here, and therefore one would have the main result, the main theorem that we wanted, under the assumption that the original random vector x has a log supermodular density, rather than the assumption that each of these ys's have log supermodular densities. So this conjecture was made explicitly by Zartash and Robeva just a couple of years ago. So this is maybe 2021 or so. The reason this conjecture is non-trivial in some sense is because it's well known that log supermodular densities are not preserved under convolution. Are not preserved under convolution, right? So just taking the convolution of two log supermodular densities does not result in a log supermodular densities. There are counterexamples that go back many years, and therefore what is of interest here is a more delicate statement that one has preservation of log supermodularity under convolution with some special kinds of distributions, in this case the Gaussian, right? So what we are able to prove is that actually we're able to prove a slightly more general fact, which is theorem, if P, I'll just say it like this, you can extend it to R to the ND for the appropriate statements here. So if P is a log supermodular density, and G is a product of log concave densities. So it's a product form log concave density. Right. So in other words, G, if you take a random vector drawn from G, then its components are independent, right? That's what the product form means, and that it is log concave. Then, then P star G solves the conjecture of Zartash and Robeva positively, because the standard Gaussian is a product form log concave density, and therefore one has log supermodularity of this convolution, and therefore one has the main result. So this this is basically an outline of the proof. There are many directions that I could expand on, for example, the log-supermodularity, or the, how to prove this first the general dependent entropy power inequality. Then error term is a nice Fisher information inequality underlying that. But I don't think it would be productive given that we are almost out of time. So let me just close with a summary. We presented a new entropy power inequality for arbitrary dependent random variables, but that has a complicated error term. But when the joint density is log supermodular, this error term goes away, and one gets this nice statement relating the entropy power of the sum to the conditional entropy powers of the summands. And in particular, we can recover the original entropy power inequality. So thank you.
Thank you, Mokshay, for a very interesting talk. Are there any questions? There's a question in the chat. I don't know whether can you see it, or do you want me to read it?
So now I can see it since I stopped sharing my screen.
Okay.
Let me see. Okay. No April Fool's Day trick. Yeah. Okay. Okay. So the as far as the definitions of entropy, I mean, the reason that sometimes this is called the Boltzmann-Shannon entropy is because this originally was defined. It was not called the entropy at that time, but it was defined in 1898 by Ludwig Boltzmann. And when he was trying to show, of course, Boltzmann was a physicist, and he was trying to show, he was studying the Boltzmann equation, which studies the evolution of molecules of a gas, right? You have a bunch of molecules of a gas in a box, and they're bouncing against each other. And, one wants to study if the distribution of positions and if the distribution of velocities of these particles comes to some form of equilibrium. And what Boltzmann observed was that this functional, the entropy, although he took it with a minus sign, he did not take the minus sign on the entropy, and he called it the H functional. So the H functional he showed was monotone. It's a Lyapunov functional for the dynamics of the Boltzmann equation. And that's how he was able to show that there is convergence to equilibrium, which is the Gaussian distribution for the velocities. And so this goes back to the late 1800s. But then it was not really, I guess, investigated in depth for a long time until 1948, exactly 50 years later, when Claude Shannon, who was an engineer, was studying the fundamental limits of communication. And he ended up using the same definition, but this time with the minus sign, because that turned out to be essential to capturing, communication across noisy channels, right? And since then, it has played an increasingly important role in probability and other fields of mathematics as well. But that's the back history. It was originally defined by a physicist, but the name was given to it by Claude Shannon, supposedly under the advice of John von Neumann. So, and apparently there was some remark of the kind: if you call it entropy, then it will become popular or something like that. So, which is turned out to be prophetic. So, and it also turns out to match up with for the physicists, there's this macroscopic notion of entropy that they had before, but this is the corresponding microscopic notion. So it's, for good reason, it's called entropy. All right.
Thank you. Are there any other questions?
Mokshay, do you hope to extend this to bigger classes, this inequality, or?
So I think this is, personally, I'm quite satisfied with this result. One cannot expect, so either you're going to have some, in general, you cannot expect an like clean form of an entropy power inequality for arbitrary dependent random variables, right? So this log supermodular assumption turns out to be a rather natural assumption that comes up here. And you know, I mean, one other reason why it's natural is because many statistical physics systems, you know, so statistical physicists are interested in proving central limit theorems, for example, for these, you know, statistical mechanics models, right? Which are typically dependent models. You have a bunch of dependent random variables, and you might have objects like this, you know, some sum of dependent random variables. But the assumption of log supermodularity is physically natural. It's physically natural, which is why the FKG inequality is so useful for a lot of statistical physics work. So it is actually a natural assumption to impose, and I don't see how one would broaden it. I mean, we do have this more general entropy power inequality, but there's this error term, and I can only see, I mean, this would be the clean way to get rid of the error term, right? But in general, that error term it's not clear how to evaluate that. So.
Another question, for this error term, you say it's above 1, right? But do you have kind of I'm not even sure, kind of a boost in some cases?
I mean, oh,
that it's
yeah.
way above
Okay.
1?
I guess it's 1. It would be okay. So that's a good question. Okay. Well, let me not say something without thinking. So yeah, not sure, but that's a good question. Yeah. I should say that we thought that we might be able to prove a more general, without the assumption of log supermodularity, that this error term, because it's an integral of Fisher information type quantities, we were massaging that and trying to prove that you can actually write it as some other, you know, measure of dependence, entropic measure of dependence. And we there seem to be some technical difficulties in completing that. So I mean, maybe we'll be able to complete that at some point. But as of now, you know, for now, we've given up on that.
Thank you.
Okay.
Mokshay, hi. This is Gautam. I have a question. You know, like there's this entropy power inequality type thing by Arras and Courtade, in which they lower bound the entropy power of x plus y in terms of the entropy power of x, y, and the mutual information. So is there a connection with this work? And
okay, so I should yeah, so I should probably have looked that up and compared. I don't remember exactly. So it actually I don't remember. Yeah, do you remember the form of the result exactly?
yes, so it's something like entropy power of x plus entropy power of y plus some term which depends on the maximum mutual information that you are allowed, times entropy power of x times entropy power of y is less than or equal to the supremum of the entropy powers over all couplings.
Yeah. So this is a more, you know, it's a different kind of inequality because you're taking a supremum over couplings, right? So whereas our goal was to get that's the difference, is that they do a supremum over couplings, whereas our goal is you're given a dependent random vector x, right? And you want to consider the entropy of the sum of its components. We're just given that we are not allowed to vary the coupling, right? So it's not the marginals that are important, it's the joint distribution that's important for us. So yeah. So right, so they have a kind of strengthened EPI which works with where you take a maximum over couplings. Right, now I remember. Yeah. Does that make sense?
Yeah. Thanks.
Thanks. Other questions? All right. If none, then let's thank Mokshay again. And I will
Thank you.
stop recording now.